I'm Cristina Rusu, and I work at Research Institute at CREO. And starting from this year, many research institutes in Sweden, they just went together in a bigger umbrella called RISE, Research Institute in Sweden. And I'm going to talk a little bit about energy harvesting and Internet of Things. We had very nice examples before, but Internet of Things and energy harvesting is not only about the harvester itself. So I assume everybody working with wireless sensor networks or networks know that you will have, let's say usually you have a battery, a power, and then you have lots of sensors, and you have a microcontroller and communication unit, and then you have on the other side the actuators and the communication. So if it usually, when you have a battery, it's quite easy, or you have a plug. You know how much power, what is the current, the voltage, so then it's easy to design. But in our case, when you want to do this with energy harvesting, will not be easy because you don't have only the harvester itself. You will have also where you have to store the energy, usually a supercapacitor, and then you have the power management, and then you have the microcontroller and the communication. So you'll have to optimize each of these components in such a way that you can say, I have an energy harvesting technology. And one of the big problems so far that you don't see so many on the market is that only harvester, you are dead. Only electronics doesn't work if the harvester doesn't work. So you need to have the whole combination, otherwise a company or industry will not take it. So, of course, batteries and plugging, it's quite useful, but which are the applications when you say that now I need to get rid of the batteries or the cables and I need to have an energy harvester, because not all application will have benefit from this. So usually, if you have, do we have even? No, that was not a good idea.
I thought I set it up so nicely.
Yeah.
A pointer is here.
Yeah, okay. So if you have large quantities, for example, sensor networks, when you have more than hundreds of sensors, for example, in the building industry, when you want to place it inside of the walls to measure, for example, humidity, or if you have leakages of the water, or if you want to have an industrial application. So big quantities and places where it's difficult to replace the battery or you have a power supply, in that moment, the alternative for the battery can be an energy harvesting. It's not me this time. So what is the main driver? So in principle, the idea is that, okay, it's everyone is talking about the trillion sensors which need power. Think about how many batteries you will eventually need if you want to go on this way. So for example, a battery, to get rid of it, is not only necessary, for example, for the automotive in the tire pressure monitoring system, where half of the whole sensor part is the battery. Think 4 of these pressure sensors on a car, how many millions of cars, how many batteries you'll have to throw away after that one. Another application for the battery to replace, it's also for the medical application. There are quite a lot of problems in the pacemaker, for example. Not only the fact that the battery cannot last as long as a doctor would like, such that you don't have to every 5 to 10 or 15 years to have an operation to replace the battery. So it will be very nice if you can have a system which can use the movement of the heart, just that, and then you have the harvester. So we have a European project on which we try to see what is possible in this area. Another application where it's good to have energy harvesting, it's, for example, when you go on the structural health monitoring, for example, for the airplanes or the cars. Because if you have many sensors, for example, put it on the airplane or on the wings, and you have all the cables around just for the testing, you'll have kilos added, which means that the testing is not done anymore in the real environment. You will have extra weight. So just to give you an example, for turbine combustion for the airplane, this is just a motor for one airplane. And usually they have between 50 to 100 sensors just placing on this one just for the testing. And how many cables? Usually it's about 20 to 50 kilometers of cables just to place on this one, just to do. So it takes a lot of time to place it. You have extra weight, and then you don't know if the data is the real one for the sensing correctly. And another point it's about, which not everybody talks about, it's about the manufacturing cost of the cables. So for example, the simple question is, how much energy it is need to produce, for example, 1 meter of a power cord, for example, for a low power temperature sensor. And if you make a simple calculation, we'll get up that you will need about 31 years you could power such a sensor with the energy needed just to produce 1 meter of cable. So there are activities which really require that you'll have to think of energy harvesting. So I think most of you already know, so the main sources for this are usually the light, photovoltaic, and we had a very nice example for indoor light. And then we have the thermoelectric, where you make use of the difference in the temperature, for example, inside of the building, outside. So you'll need few degrees in such a way that you can use it. And then we have the kinetic or vibration, where, for example, you can have the piezoelectric, where due to piezoelectricity, the bending of the material will make that the charges will separate, so then you create an electrical voltage, and that it's a reversible, so it's a very good method. Or you have the radio frequency or inductive, like you have, for example, with the toothpaste, the electrical toothpaste. So if we go further to, it's not so clear, about typical output power and the harvested energy, you can see that unfortunately so far the efficiency is quite low. And if we look for the energy harvesting, for how much do we need, in principle as a power, we are still in the microwatt, milliwatt, if we look for the not really consumer application, but what exists at this moment on the market. So there are very few companies really on the market with this one. One of the good things is that electronic people are working hard to reduce the power consumption, because if you have all the electronics, and just to start an electronic, you need a certain current and a certain voltage, otherwise the electronics will not start. So then it means that you need a lot of harvesting energy to be stored and then further. So it's good that energy harvesting becomes a little bit more evolved, but also the utilization and all the design for the electronics is made in such a way that we can still combine the two. For example, for the communication, there are lots of protocols, and unfortunately at this moment we are still in this area for communication. We can't use everything because it's about how much data we transfer, how often. So that it's a lot of work done also on the computer science. How do you compress the data? Do you send the raw data? Do you do on the local compression, or you make the data analysis there, or you do it on the cloud? So lots of work is done also for communication also. So if we look to the challenges, in principle, energy harvesting is quite a new technology, even if we think that, for example, RFID, it's already known for quite some 10 years, but still doesn't exist enough infrastructure to say that it's already a standard method. So requires a lot of significant process miles, especially on the power density. And of course, a lot of work needs to be done to get a very ultra low power electronics, and then for the storage of the energy, but also for the communication, for the standards and data transmission. So I'm glad that a community of researchers are working in all these areas such that together we can come to some viable solutions. And of course, the energy harvesting still faces technological challenges like the electromagnetic are still big. You can't have it easily in small, for example, in an... is this working, the timer? It still shows 5 minutes, okay. Electrostatic are just too little energy producing. Piezoelectric films at this moment is difficult to get powered from, and also the thermal, it's quite costly. So as a summary, still energy harvesting are facing a strong competition from the batteries. However, it's not always needed to just replace the battery. It's enough if you have a harvesting which will continually help the battery to extend the lifetime. Because many in industries, they are worried about, okay, you will make a very nice harvester or electronics now. What about 20 or 30 years? Because automotive or aeronautics, they'll have components which have to be alive also after 30 years sitting on a shelf. How many floppy disks can we read today? Nothing. So if the same will happen with the energy harvesting components, will be useless in 20, 30 years. So industry will not take it up and will not give any help in the development if we don't show that we know how to design for the future and how to, from the testing we do at this moment, we can have prognosis and design rules to be still valid over 20 or 30 years. So one of the big problems at this moment are the reliability. They are not so easily and continuous power, and then we have the standardization. Everybody designs their own, and then it will be difficult to combine with components, so that will be still needed. It seems that I still have time, so I was thinking just few minutes. So for example, if we take for optimization of the kinetic piezoelectric, we have to know how do we lose efficiency and losses? So we have the coupling efficiency between the ambient, the source of the energy, and then your moving mass, for example, and then you have the transduction efficiency, how much do you lose from mechanical to electrical, and then the electrical to the power. So there are all these small things you have to know about them. And then about the piezoelectric material, for example, how the crystallographic and texture of the piezoelectric material influences the reliability, the reproducibility, the process control. So it's material science, it's electronics, it's mechanical design, so it's a really a together family. So one person or one subject is not enough. And for the energy storage, for example, also it's very important because what do you do with a harvester without putting somewhere the energy? So for example, thinking of sustainability, Chalmers works with the cellulose to try to make the whole supercapacitor using cellulose material for electrodes and for the membrane in between. And of course, the very low power electronics, and will be a quick presentation later about electronics, about this one. So, thank you. So that was just a taste of how much work we still need to do.